Thank you for your introduction. And I'd like to thank the organizers for giving me the opportunity to talk in this wonderful conference. I'm a statistical physicist and at the same time, a little bit of a quantum physicist. So today I'm going to talk about fundamental aspect of the relationship between quantum thermodynamics and quantum information theory. Especially, I will focus on quantum fluctuation theorem and the measurement and feedback performed by so-called Maxwell's Demo. So this is the outline of today's talk. So my main topic of this talk is about the thermodynamics of quantum continuous measurement and feedback. But before going there, I will review some key results developed in this decade, starting from the classical thermodynamics, and then I will go to quantum thermodynamics, and then I will go to the main part that is about the continuous quantum feedback control. Okay, so let me start from a very general introduction to this topic. So the background of this topic is known as Maxwell's Demo. It is actually a very old topic. It dates back to the 19th century. So, but from the modern point of view, the Maxwell's Demo can be regarded as a kind of feedback controller about the thermodynamic system that performs a measurement and the feedback at the level of thermal fluctuations. By doing so, the second law of thermodynamics is apparently modified by incorporating information terms. So we can understand some fundamental aspects of the second law of thermodynamics, and maybe we can apply thermodynamics of information to nanomachines and nanodevices, both artificial and biological. Okay, so this is a simplest model of Maxwell's Demo. So this is just a single molecular gas confined in a box, and the box is in contact with the thermal heat bath at temperature T. So this is a very, very simple model, but we can quantitatively understand the relations between information and thermodynamics. So let me briefly introduce this model. So first, the particle is in a box, and the box is in thermal equilibrium. And then we insert a barrier or the wall at the center of the box. And at this stage, we don't know in which box the particle is. And then the demo performs a measurement, and it finds the particle in the left box or in the right box. That information is 1 bit because we have two possible outcomes, left or right. That is corresponding to log 2 of information in the natural logarithm. And then the demo performs a feedback control. If the particle is found in the left side, then the demo does nothing. But if the particle is found in the right side, then the demo moves the box to the leftmost side very slowly. This process doesn't require any work. And finally, we expand the box here to here, and the gas returns to the initial state. During this final expansion process, we can extract KT log 2 of work because we can calculate this by using the equation of states of a single molecular ideal gas. So the entire process is cyclic, and there is just a single heat bath. This is apparently looks like a perpetual motion of the second kind, but actually it is not. And the essential mechanism of this Strato engine is very simple. So we can just reduce the entropy by log 2 by performing the measurement and feedback during this process. And the decrease of entropy implies the increase of the free energy, and the free energy is the resource of the work. So finally, we can extract KT log 2 of work during this process. So the key point is that the obtained information log 2 is proportional to the obtained work KT log 2, and the proportional coefficient is given by the Boltzmann constant and the temperature. So the message is that we can control physical or thermodynamic entropy by using information via measurement and feedback. Okay, so nowadays there are many experimental realizations of Maxwell's demons, and these are just two of them, and there are a lot of experiments both in the classical and quantum regimes. So now we can say that Maxwell's demo is a not only theoretical but also experimental issue in statistical physics. Okay, so now today's main topic is this. So and we have a lot of generalizations of the second law of thermodynamics in various setups, both in classical and quantum cases. And there are basically two situations. One is just a single measurement and feedback, as in the original Maxwell's demo. And the other is a continuous measurement and feedback. This is practically more interesting situation. So our main result is the latest paper published here. That is about the thermodynamics of continuous quantum measurement and feedback. But before going there, I will briefly review these other results step by step, starting from this classical single measurement and feedback case. Okay, so in the classical scenario, the most important quantity in thermodynamics of information is known as mutual information. As a mutual information quantifies a kind of correlation between these between two systems. In the context of Maxwell's demo, the system S is measured, and the measurement outcome is stored in a memory. Memory is a kind of for example, a brain of Maxwell's demo. And the effective information obtained by the demo is corresponding to the correlation between the system and the memory. And that correlation is quantified this mutual information that is defined as the sum of the Shannon information of the system and the Shannon information of the memory and minus Shannon information of the joint system. So, and the mutual information satisfies these two inequalities, and the maximum value is given by the Shannon information, and the equality is achieved if there is no measurement error here. And one of the basic results of thermodynamics of information in the classical case is that the upper bound of the work that can be extracted from the engine in the presence of Maxwell's demo is given by the mutual information. So without Maxwell's demo, then it is well known that the upper bound of the work is bounded by the free energy difference of the engine. But if there is a Maxwell's demo, you can extract more work than the conventional bound, and there is a new bound, and this new bound is exactly given by the mutual information. And it is known that this equality is achieved if we can cleverly design the feedback protocol for a given mutual information. So in that sense, this is a kind of optimal inequality that we can achieve, and this gives a generalized second law of thermodynamics by incorporating the mutual information term here. Okay, so this is already more than 10 years ago result. So, okay, sorry. So before going to the next step, so let me just discuss more intuitive meaning of this information heat engine. In the conventional scenario, the work is extracted from a part of heat flow between two heat passes at different temperatures. And the upper bound of the heat, the efficiency of the conversion from heat to the work is given by the Carnot efficiency, as is well known. And the upper bound is achieved by the Carnot cycle, that is a reversible heat engine. On the other hand, in our scenario of information heat engine, the resource of the work or the free energy is given by mutual information, and upper bound of this conversion rate is given by the zeroed engine. Actually, in the case of the zeroed engine, the work is given by KT log 2, and delta F is 0 because it's cyclic. And the information is log 2. In that case, the measurement is error-free, and the mutual information is just same as the Shannon information. So we have log 2 equals log 2 here, and the zeroed engine gives the maximum conversion rate from information to the free energy. So in that sense, so the zeroed engine is a kind of a very fundamental building block of information thermodynamics that plays a parallel role to Carnot cycle in conventional heat engines. Okay, so Okay, so now we are going to more non-equilibrium aspect of this thermodynamics. So in 1997, Jarzynski found that there is a kind of universal equality from which we can reproduce the second law of thermodynamics. That is called the Jarzynski equality. So the Jarzynski equality is given by this, and which is given by the ensemble average of exponential minus work and the free energy. So the impressive point of this equality is that even if we can drive the system far from equilibrium, we always have a equality here instead of a conventional inequality as in the second law of thermodynamics. So this means that if we sum up all orders of fluctuations, then the second law of thermodynamics can be indeed expressed in terms of equality. So actually, if you expand the exponential inside the ensemble average, you will have the second and third and fourth orders of fluctuations. And if you sum up all of them, we have a universal equality like this. And by applying the convex inequality or the Jensen's inequality here, then we can reproduce the conventional second law of thermodynamics. On the other hand, as I have shown in the previous slide, we have a generalized second law of thermodynamics in the presence of Maxwell's Demo, given by the mutual information. So the question is that, is there any generalization of the Jarzynski equality to the feedback processes? Here. So our answer is that if we put the stochastic mutual information term inside the ensemble average, then we can recover the Jarzynski equality in the same form as in the conventional case. So this is the definition of the stochastic mutual information. So X is the system state and Y is the measurement outcome. And the ensemble average of this quantity is just the ordinary mutual information. And if we put this stochastic quantity here, then we recover the same form of the Jarzynski equality. On the other hand, if we drop this mutual information term in the presence of Maxwell's Demo, then the left-hand side is deviated from 1, and the conventional Jarzynski equality is violated. So we can say that even if there is a Maxwell's Demo operation, like measurement and feedback, we have the same structure of non-equilibrium statistical mechanics, like the Jarzynski equality, if we take into consideration the mutual information term here. And we can also apply the Jensen's inequality here, and we can recover the second law of thermodynamics at the level of ensemble average. Okay, so this is, so far we have considered the work and the free energy. So next, I will slightly generalize this situation to more non-equilibrium case. I mean, if we start from a non-equilibrium, highly non-equilibrium state of the system, and we can end up with another non-equilibrium state of the system. In that situation, the work and the free energy are not so good quantity to characterize irreversibility. Instead of that, we can introduce a concept called the entropy production. So entropy production is given by the difference between the system's channel entropy change and the heat flow from the heat bath to the system. So this is the definition of the entropy production, and it can be shown that this is always non-negative. And this is the second law of thermodynamics. And in a special case that if the initial state of the system is in thermal equilibrium, like the Gibbs state, then this entropy production reduces to the work and the free energy. So in that sense, this is a slight generalization of the previous scenario to more non-equilibrium situations. And we can also introduce a stochastic version of the entropy production. So originally, the heat is a stochastic quantity because there are a lot of thermal fluctuations around the system. And we can also introduce the stochastic channel entropy like this. So this P is the system's probability distribution. And this is so-called the self-information of this probability distribution. So then by using this stochastic channel entropy, we can define the stochastic entropy production rate like this. And then we can have the same form as the Jarzynski equality like this. This is called the fluctuation theorem. And from this, again, we can apply the N-sense inequality, and we can get the second law of thermodynamics at the level of ensemble average. Okay, so now we can also introduce the Maxwell's demo operation here in the formulation of the entropy production. And we have the same form of the generalized fluctuation theorem with the entropy production and the stochastic mutual information term here. And in this formulation, the generalized second law is written as this. This means that the lower bound of the entropy production is now not given by 0. Instead, it is given by minus of the mutual information. So this is the same as the work inequality that I have shown before if the initial state of the system is in thermal equilibrium. So this is a general form of the second law of thermodynamics. And in the presence of Maxwell's demo, that performs a single measurement and a single feedback control. Okay, so this is the first part. And then we are going to more interesting situation, but still classical. So this is, for example, we consider our cells or some bacteria, then there is some autonomous information processing. Because in our cells, for example, there is no external Maxwell's demo, or there are no external driving from the outside. So we can consider that a kind of Maxwell's demo is implemented inside the cell. For example, in this bacteria case, we can consider that the methylation level is a kind of Maxwell's demo, and that performs a feedback on a kind of kinase activity or something like that. So in such a situation, the entire operation of Maxwell's demo is completely autonomous. And so we need to formulate thermodynamics of such a autonomous information processing processes in which a measurement and feedback are continuous in time. So we can separate measurement step and the feedback step clearly, but instead they occur at the same time. And we have some continuous information flow instead of just a snapshot mutual information. So mathematically, we need to introduce some continuous version of mutual information. So, and there are several approaches. So one is known as the transfer entropy approach, and the other is known as the information flow approach. In this talk, I will focus on this transfer entropy approach because it is easier to generalize the second law to the quantum situations by using this transfer entropy. So yeah, so this is our classical setup. So we have two variables, x and y, and we can imagine that y is a Maxwell's demo and x is a controlled system. And the transfer entropy quantifies a kind of directional information transfer from x to y. So the mutual information cannot characterize any directional information flow because it's symmetric between two systems, x and y. But in this case, we consider conditional mutual information under the condition of this y of t, and we consider the correlation between x of t and y of t plus dt. So this means that the system y obtains new information during this infinitesimal time step dt about the system x. So yeah, because we have a conditioning here, so this can describe a kind of directional information flow from x to y. And we can normalize it by dividing it as dt. And this is called as the transfer entropy rate. Historically, the transfer entropy was introduced by Schrieffer in more general form in 2000. And actually, it can date back to 1950s, I think. It is known as the Granger causality in economics. And it won a Nobel Prize of Economics many years ago. But in our context, we just consider this quantity, and this is just a conditional mutual information. Okay, and I'm not going into the details, but by introducing the transfer entropy to thermodynamics, we can even generalize the second law of thermodynamics for continuous information processing situations. So yeah, this is a stochastic transfer entropy, and this is a second law. So the entropy production is bounded from below by minus of transfer entropy. And we have in this paper in 2015, we have applied this second law of thermodynamics to analyze some bacterial chemotaxis. But anyway, so far I have reviewed the classical part of this topic. So then I will go to the quantum aspect of thermodynamics of information. So, but okay, so in quantum thermodynamics, so there are many interesting experimental platforms. For example, trapped ions and superconducting qubit and single electron. It's often classical, but can be quantum, and also NMR. So there are several experiments that implemented Maxwell's Demo in the quantum regime. For example, in this case, the demo performs a quantum measurement about the system and then performs a feedback control. And so next, our goal is to formulate the second law of thermodynamics in the presence of quantum measurement and feedback. So actually, both in the classical and quantum regimes, thermodynamics are very similar, but we should only replace the mutual information term with a kind of quantum information term like this. So this is called the QC mutual information. So in our situation, the system is classical. In our situation, the system is quantum, and our measurement outcome is classical. So we need to characterize the correlation between the quantum system and classical outcome. So that's the reason why we named this as a QC quantum to classical mutual information. So this is also known as the Grunewald information, but it was originally introduced in 1970s by Grunewald. And this is a little involved, but essentially given by the difference between the von Neumann entropy of the measured state and the von Neumann entropy, average von Neumann entropy of the post-measurement state. So this MK is the measurement operator or the Krauss operator, and this is the post-measurement state with outcome K, and PK is the probability of obtaining outcome K. And the QC mutual information satisfies these two inequalities, and the upper bound is given by the Shannon information of the measurement outcome. And the equality here is achieved if the measurement is error-free and classical. Error-free means the measurement operator is given by the projection operator, and the classical means that the projection operator is commutable with the measured density operator. Okay, and again, we have the same form of the second law of thermodynamics in the quantum setting, just by replacing the mutual information with the QC mutual information here. And again, this is an achievable inequality. I mean, the upper bound can be achieved if we cleverly design the feedback protocol. So in that sense, the QC mutual information is a kind of proper quantity to give the upper bound of the extractable work by Maxwell's Demo. Okay, so then we have also the generalized Jarzynski equality by introducing the stochastic QC mutual information. So this is very involved, so I will skip the details. But we have essentially the same structure as in the classical case, but we need to replace the mutual information, stochastic mutual information term with the QC mutual information term, stochastic QC mutual information term here. Okay, so these are the review parts of previous key results. So then I'd like to go to our main latest result about the continuous quantum feedback control. Okay, so these are collaborators of this work, and Toshihiro Yada is my master student. He's here and yeah, sitting there, and Nobuyuki Yoshioka is a research associate of my group. Okay, and So this is the same slide as I have shown before. So I have talked about the classical single and continuous cases and quantum single measurement and feedback case. So the main result of this talk is about the quantum continuous measurement and feedback case. And in every case, we have the same structure of the second law of thermodynamics and the fluctuation theorem. So the entropy production is bounded by minus of some information term, and the fluctuation theorem is given by exponential minus of entropy production minus some stochastic information term. And but we should properly choose the information term for each case. For example, in this case, just a mutual information, and in this case, classical transfer entropy, and in this case, QC mutual information. So as we can expect, we can introduce a kind of QC transfer entropy here. Before going to that, let me just emphasize why quantum continuous measurement and feedback is so important. So in dissipative quantum systems, the system, the quantum nature is lost because of some decoherence or something. If we want to maintain that quantum feature, so we need to keep the state by performing continuous measurement and feedback. For example, in this example, they prepared a Fock state by using quantum measurement and feedback. This shows that we can also use the continuous quantum measurement and feedback as a kind of state preparation of quantum systems. Okay, so now to analyze the thermodynamic properties of such quantum measurement and feedback continuous situation. So we have introduced a new quantum information content that we name the QC transfer entropy. So this is a total information transfer by continuous measurement. And I will show the definition in the next slide. But anyway, so the basic structure of the second law and the fluctuation theorem are the same as in the conventional cases. And the entropy production is bounded by minus of the QC transfer entropy, and the generalized second law is given by this stochastic QC transfer entropy. Okay, so this is a mathematical definition of our setup. So we have a quantum system here, and we have a heat bath here, and we have, in addition, we have some measurement apparatus to perform continuous measurement and feedback. And these two external effects are both described by the Lindblad master equation. So this orange term is a Lindblad master equation corresponding to this heat bath that satisfies the detailed balance. On the other hand, this green terms describe the effect of measurement apparatus, and this is also given by the Lindblad equation. But now it is given by a stochastic version of Lindblad equation that is called also the stochastic master equation, because we have measurement outcomes from the measurement apparatus. So and the measurement outcomes are randomly obtained. So the conditional density operator obeys a kind of random or stochastic time evolution under the condition of some random measurement outcomes. So that random effect is described in this delta n term here. So this represents the some Poisson increment obtained by the measurement. Okay, so and also the feedback term is represented by this gray Hamiltonians, and these Hamiltonians can depend the past measurement outcomes. So that is the effect of feedback control. Okay, so now we define the QC transfer entropy. So in the classical case, the transfer entropy is described by conditional mutual information under the condition that we have a measurement outcomes in the past, and we define the conditional mutual information between the system and the next step measurement outcome. So now we define the conditional QC mutual information between the system and the measurement outcome at time n+1 under the condition of the past measurement outcomes until time tn here. So this is a very natural quantity because we already have a kind of conditional density operator here, because if we solve the stochastic master equation, we have a conditional density operator. So by using that conditional density operator, we can define the QC mutual information here. And if we sum up it from time 0 to time t, then it is nothing but the QC transfer entropy. Okay, so next we want to introduce a stochastic version of QC transfer entropy. So this is the most tricky point of this work. So because in quantum setting, the concept of conditioning is very non-trivial. And also we have we need to introduce some other variables that I will explain from now. So this is the original setup. So we have the system and the heat bus here and the measurement apparatus here. But in order to introduce the stochastic QC transfer entropy, we need to perform additional projection measurements on the system. So for that purpose, we first mathematically deform this setup to this one. So this is nothing but the Trotter decomposition. So we just shift the timing of the measurement and the dissipation into the heat bus. Then we insert some projection measurements immediately before and after the measurement by the apparatus. And we get some measurement outcomes, P, Bn, and Cn. An important point here is that the projection measurement is performed in the diagonal basis of density matrix before and after this measurement Yn. So because this is a projection measurement in terms of the diagonal basis of the density matrix, so this these projections do not destroy the ensemble average dynamics of the density operator. So this can be regarded as a kind of an artificial step to reconstruct the QC transfer entropy from measurement outcomes. And I would like to also emphasize that these projections are very strong measurements, but the QC mutual information is still convergent by applying the sequence of projection measurements, because during these measurements, the state change of the system is infinitesimally small. So we can, if we sum up the information about the system, we still have a convergent term. Okay, so now we have the original setup here, and we deform the original setup, and we insert some projections here and there. So then we can define the stochastic QC mutual information. But in real experiments, it is not so easy to introduce these projection steps because these are very strong measurements on the system and strong and continuous measurement steps. So we have proposed some experiment-numerics hybrid method to test our fluctuation theorem. And that means that the original real experimental setup is given by this. And we have dissipation and measurement apparatus. And we have some trajectory from real experimental data. And then we can numerically reconstruct the density matrix based on the real experimental results. And then we can artificially insert these projections. Then we can have the entire information to obtain the fluctuation theorem and the QC transfer entropy. But in some cases, if the measurement setup is very good enough, then sometimes we can perform these projections in real experiments. But anyway, in general, we can consider this hybrid experimental numerics hybrid method to get our result. This is a numerical simulation of our results. So this is the second law of thermodynamics. These orange circles describe the entropy production, and these are negative. This implies that the ordinary second law is violated as a consequence of the feedback control. And these green circles, it's a QC transfer entropy, and this is below the entropy production. So this means that the generalized second law is satisfied. And this is the generalized fluctuation theorem. So if we don't take into account the QC transfer information term, and if we just naively consider the exponential minus entropy production, then the conventional fluctuation theorem is violated as this is deviated from 1. On the other hand, if we consider the QC mutual information term inside the exponential and the ensemble average, then we always have 1 like this. So this means that the generalized fluctuation theorem is indeed satisfied in our numerical demonstration. Okay, so this is the summary. So in the quantum system under continuous measurement and feedback, we have introduced that we have generalized the second law of thermodynamics and the fluctuation theorem by introducing the QC transfer entropy. And we have proposed the experimental and numerical hybrid method. Okay, and these are references, and the main result is here. And these are some backgrounds, both classical and quantum. And these are review papers about the classical and quantum cases. And finally, let me just advertise my book. So I have published a book this March, I think. So this is about some mathematical theory of thermodynamics. That's it's more mathematical than the so-called information thermodynamics. But I have focused on some general properties of entropy and divergence and so-called majorization. And I discussed its relationship to classical and quantum thermodynamics as applications. So this is almost mathematical book. It's a kind of definition and theorem and proof style. But if you are interested in, so you can also see it on archive. But there are several mistakes still there because it's just a draft. Okay. And in the published version, these mistakes are, of course, all corrected, I think. Okay, so this is the end of my presentation. Thank you very much for your attention.
Yeah, we have time for questions. Yes.
Thank you for your talk. A question about this trotterization, which you discussed on some slides before.
Yeah.
And where you splitted the integration, I guess, into two. You applied this trotter sequence of.
Yeah.
Right. So my question is, since these two steps or these two operators usually do not commute with each other, there is a small error.
Yeah.
And can you comment on the impact of this error on the outcome of your calculations, and how important is that, if any, if there's any importance?
I see. Yes. Yeah. In general, so these two processes are not commutable. So there is some small error. So in the delta t equals 0 limit, of course, they are equivalent. But in, for example, in numerical simulation, there should be some remaining error. But I think in our numerical result, so the effect of that error is not visible here. And yeah, the error bar is also hidden in the plot. So I think this numerical result is very accurate, and this can well reproduce the ideal limit delta t goes to 0, I think.
Can you quantify these errors as a function of delta t?
Actually, we haven't done it, but I think it can be, yeah.
Thank you.
Can be avoided. Yeah.
Okay, so any other questions? Yeah, so Professor Gawa, I have one question. You know, this numerical results, what is the specific setting for doing the numerics?
Oh, yeah, sorry, I haven't written down. So this is about some two-level system, and
Two-level
it
system, okay.
performs a measurement about that system. And we, for example, we flip the population if we found the system in the excited state, for example.
Okay.
So, yeah.
Yeah.
Sorry, I haven't prepared that slide. But
Okay.
I think my student will present a poster presentation this afternoon. So
I see. Yeah.
Yeah.
Okay. Is there any relationship with the quantum information science, in your result?
in other information,
In terms of applications in quantum information science, what do you see that
Oh.
your result can be applied in that field?
yeah, I expect that some transfer entropy, QC transfer entropy is useful for other situations. In fact, not transfer, but the ordinary QC mutual information has some good theoretically good properties.
Okay.
Like, it gives a kind of the upper bound of accessible information or something like that. So we can expect that the transfer entropy has the same kind of meaningful properties.
Okay, great. Yeah. Any other questions? Yeah, please. We still have time for questions. Yeah. All right. If not, let's thank our speaker again.